Go ahead. Now you can.
Good afternoon, everyone. It is my pleasure to introduce two of our colleagues here, Eugenia Etkina, Professor of Physics Education, and Josh Rutberg, who's a graduate student working with Eugenia. And they're going to talk about the work that Eugenia certainly led in developing a science, physics learning environment and in undergraduate education. And so just let them take it away. Thank you.
Okay. Go ahead, Josh.
I'm making sure to restart the timer. I know you
Oh,
want to do that.
okay. Yeah, good.
All right. Welcome, everyone. My name is Josh Rutberg. I'm a PhD student here in the LSIT program, working with Professor Eugenia Etkina. And we just wanted to take some time today to share with you what's been going on for the past nearly two decades and what we've been doing with the investigative science learning environment here at Rutgers.
So before we start, I want you to look at your table and see what's there. So what do you see? Scales, right? So what I want you to do is look at the scales. Are they the same or different? Slightly different? You see they're slightly different, right? And if you pull, you can see one is a little softer than the other. So these are different scales. I just want to make sure that you agree with that, right? Okay, so I want you to place them flat on the table like this and make sure that each of them is zeroed. And if it's not zeroed, there's a little pull thing on the top that allows you to pull it. So if they're zeroed, what I want you to do, I want you to hook them up like this. You hook them up, right? And then one person is doing nothing, just holding the scale, and the other person pulls, and make sure that you look at the reading. Don't pull beyond the stretch, but somewhere to 1-2 newtons on the scale, and don't pull too hard. You already pulled too much. Right. Then I'm not sure if you, yeah, if you already got it. It's a 2. It's a 2. Yeah.
Start again. Yeah. Start again. It's not a 0. It wasn't.
Yeah.
Yeah.
Do not pull all the way. Pull to 1 or 2.
Well, why don't you?
Okay. Why don't you take this?
Yeah. So what is it reading? Right. So this is
Right. So both read. So and then pull slightly differently. You know, the other person pulls. What are you noticing? What are you noticing?
The same grams.
The same reading, right? Doesn't matter who pulls, right? So what are the scales reading? One scale reads the force that the other scale exerts on it, right? And although only one of you was pulling, both scales showed the reading, right? Well, you managed to break this one too. So the students do the same exact experiment, and we ask them, you know, what do you notice? And they say the scales are reading the same. So what can it possibly mean? That no matter who pulls, the scales are reading the same. What can it possibly mean? Any ideas? Huh? Okay, well, you're being shy. I understand. The students have lots of ideas. And they usually say, well, it looks like though only you were pulling, with one scale, the other scale was pulling back, right? So when one scale pulls exerting 2 newtons, the other pulls back exerting the force of 2 newtons, which is okay for the scales, but is it a general rule? How can you test it that when 2 objects interact, no matter who exerts a force, the other object will exert the same force in magnitude? And so the students are given cards with in the labs with sensors, but for you sensors will not show much. So we show this is the spring that will compress if somebody hits the card. It's a plunger. Okay? So they're given the cards and they asked to test their idea of the scales exerting the same forces on each other with the colliding cards. And although their idea is that the forces are the same, they think, oh, of course the card that is heavier will hit harder than the lighter card. The card that is moving will hit harder. So they don't really believe that this is a universal idea. But we teach them to make a prediction based on their hypothesis. So they say, we'll predict that on two cards, the forces will be the same. And here the forces will be indicated by the squishes of these plungers. But they don't really believe in it. So they design all kinds of experiments, different masses of the cards, different speeds, and I'll show you one of the experiments. So this is one card, right? I'm going to play the video. You will see slowly the second card approaching. And you will see that the second card is loaded with metal blocks. So not only that it's moving and the first card is not moving, but it's also much heavier. So you would, if you don't believe in the rule you just created, you would think that that card will compress the plunger of the red card much more than the red card will compress the plunger, right? So, but look at the outcome. So this is, they start, watch the plungers. So at every instant, what do you see?
They're retracted the same.
They retracted the same. So the red card that is light and stationary manages to push the blue card that is moving with heavy blocks as hard as the blue card pushes the right one. So what they do is use the force probe sensors that give them graphs on the computers. This is the two cards, and one is almost 10 times more, no, less than 10 times, 6 times more heavier than this one. And you see that at every instant, two forces are exactly the same. So that's, and they try for hours. You know, they put some padding, they put magnets on the cards, they do everything. And to their surprise, the forces are always the same. And they say, well, this is really crazy, but the cards always exert the same forces on each other. And that's how they construct one of the most fundamental laws of physics, Newton's third law. And so this is the main idea of what we're going to talk about, the investigative science learning environment approach, which is an example of an intentional approach to curriculum design. So what is intentionality? Intentionality is the understanding that the medium through which students are learning sends the message as important as the knowledge itself that is being developed. So not only the knowledge is important, but the medium through which it is delivered. So think about, for example, now flipped classroom. Students read the textbook, then they come to class and talk about it. What message does this medium send? That knowledge comes from authority. So you learn from authority, and then you go and talk about it. So that contradicts a lot of what is done in science, but the message is very strong. So the intentionalities of IEL there too, that students do not learn physics from authority. They learn physics by practicing it just the way we discovered Newton's third law. I could have written an equation on the board and said, this is, you know, for every action, there's an equal and opposite reaction. That's what people know. But that's not how students learn through IEL. It's not only in college. We use it in middle school, in elementary education, in high school, everywhere. But at the same time, the idea that students not only develop Newton's third law, but they develop confidence in themselves and growth mindset. How does it happen? Through many different elements. And so first, to learn anything, students start with observation experiments, just like you did. You didn't predict what the scales will read. I just asked you to play and see what is happening. And identify patterns. We all saw that two scales read the same no matter who we came up with a pattern or a model of the same forces that two objects exert on each other. And we propose the testing experiments and make predictions based on the models, even though sometimes we don't believe that this is what's going to happen. And this happens very often, that first, the students have difficulty making predictions based on the idea and the test. They want to engage their intuition. But secondly, they will say, yeah, this is what should happen, but it won't. Running testing experiments means comparing prediction to the outcome. When the outcome does not match the prediction, you have to think, what do you need to revise? Either your model was not correct, maybe you didn't collect enough data to even make the model, maybe there were some additional assumptions, like the scales were pulled too hard at the beginning and were broken, you can't trust them, you need to reset them, right? But if the outcome matches the prediction, then you test it again and again. That's why the students spend an hour and a half trying to rule out this crazy idea. So imagine you have a boxer that weighs 300 pounds and a boxer that weighs 300 pounds. When the big guy hits the small guy, he gets the hit of the same force back. This is a totally counterintuitive idea, and that's why students spend hours and hours trying to rule it out, and that's the purpose of the testing experiments, not to prove, but to rule it out. And finally, when they can't rule it out, they solve practical problems with the application experiments. We have textbooks based on this approach. We have a book now written, how to do it. But this flow is not the only thing that IEL is about. Students work not only with experiments in mathematics, but with a whole library of different representations, pictures, and specific graphical representations that help them reason. I'm not going to go into details, but I'm just trying to say that we expand the representations usually used in physics, words, experiments, and mathematics, which are all very abstract, to have a bridge of concrete representations. But most importantly, that students work in small groups like you did, in groups of 3 or 4. They form a learning community through different activities purposefully organized, and they can resubmit their work, get a better grade without punishment, which is a crucial idea, that it is important when you, what you learn, not the time when you learn. So it is important that all physics experiments that usually are seen as demos and labs, raise your hands, those who took physics. Right? Remember demos and lecture and labs, cookbook labs, right? So we don't have this approach. We group all experiments into 3 categories. Observational, when students, if what you did was an observational experiment. You do not make predictions. You observe and look for patterns and then try to explain. Testing experiments, that the cards that I told you and showed you. And application experiments, when you build something based on the ideas or solve a practical problem based on the ideas that you tested. So example of experiments that the students do, you just did one with the scales, but you can do the same in electricity. You can test these ideas and you can design experiments to apply. Don't worry about understanding them. I'm just trying to show different, not only for Newton's third law, but for every single concept, we have a slew of these experiments. And what is important, that the IEL approach is an example of a universal design for education. Have you heard about universal design? I was born in the Soviet Union. We did not have, I've never seen any disabled people. Why? Because they couldn't leave their houses. We did not have elevators in most buildings, and we did not have ramps. So in order to go anywhere, you had to have crutches if you were, if you couldn't walk, and then you had to jump over the steps. So people who could not walk were told, well, just get crutches or get a stick. So the system was trying to fix people, right? The idea of the universal design, you don't fix people, you fix the environment, right? We have ramps, we have buttons for blind people in elevators with Braille, we have this ramps on the sidewalks, not only for you to roll in a wheelchair, but if you're blind, you know what's coming with this bulbs. So everything that is done in architecture, the purpose is to fix the environment that everyone can use it. But it's important that not only disabled people, you know, those who can't walk, for example, or blind, benefit from it. Everybody benefits from it. If you have a stroller with a child and now there's a ramp, you can actually go there. You don't have any physical impairments, but you benefit, right? So all the changes that are made through universal design benefit everybody. So you can think of physics that is considered one of the most difficult subjects, and the DFW rates in physics courses on average are close to 50%. So every second person fails a physics course in college, right? Eventually about 60%. So that tells you that about half of the population are not suited, are not fit, are in a way having some impairments towards physics. So instead of fixing the students and telling them you need to do more math, you need to work harder, you suffer from lack of motivation, we fix the environment. And so the IELTS approach is an example of a fixed environment. When you worked with the scales, you didn't need any prior knowledge, right? No, pull the scales and do the reading. So everybody starts on the same page. We did not use any fancy language at the beginning. So those who had some prior experience do not have an advantage over those who didn't. So we leveled the playing field at the beginning for the students. If you're weak in math, we have tons of different representations to help you, and you build confidence slowly. Students discuss the ideas and test them right away. So testing, the purpose of testing is actually try to rule out, not to prove. So when you rule out your idea, you feel successful instead of feeling like a failure. Everybody progresses at their own pace, because if you didn't get it now and you did poorly on the quiz, you can always improve and resubmit and reflect what you didn't know and how you learned it. And you improve your work without punishment. Finally, you are continuously working with the community and with a shared expertise, and you develop productive habits. And I will talk about it a little later. But it also tells you that this approach is very difficult, right? If you think about teachers who mostly used to teach. In this approach, you don't teach. You engage students in learning, and it means you need to know how to motivate them, you need to know how to make them work in groups, how to share, how to become confident. So it's really, really difficult. So instead of focusing on yourself, this approach makes you focus on the students. You need to be aware of what students think. So you need to learn how to listen to them without interrupting them. You need to know these new representations and the new language that doesn't confuse the students that we develop. You need to be skilled in facilitating group work. You need to know how to build a community. You need to believe that every student can succeed, because otherwise there's no point. And finally, you yourself need to know where knowledge comes from in order to help students construct their own knowledge. So you need to know a lot of history of your discipline. And I also remember I said that this approach helps students develop habits. So what habits do we want them to develop? So if you think about all your science courses, probably all professors started that we want you to develop critical thinking, right? That's the goal of the course. But what is critical thinking? It's a very elusive, general idea. So it's like I tell you, I want you to be able to drive with a stick, and you've never drove a car with a stick, right? Stick shift. So you need to know a lot of small operations in order to be able to do it. And eventually you do it automatically. When we think about critical thinking, it's not an automatic thing, right? It is a thinking process. But you need to know what it consists of and how to develop it. So what we did a long time ago in 2003, we interviewed many physicists about what they're doing, and we created a list of scientific abilities that we want our students to develop. The word ability is kind of confusing because people think of ability as something you're born with. But in our approach, it means completely different. You can think about a progression of knowledge, ability, and skill. Knowledge, it means you know that you need to do it. Ability means you know how to do it, but you still need to think about it. And skill means you do it automatically. So abilities is between knowledge and skills. Not only that you need to know that you need to do it, you need to know how. And so after the analysis of what physicists do, we came up with a list of what physicists do, what they're able to do, but not automatically. They represent information in multiple ways. They design and conduct experiments to investigate the phenomenon. That's just what you did. They also design and conduct experiments to test phenomena, explanations, design, conduct application experiments. These are all parts of the IELTS process, right? They collect and analyze data. evaluate models, equations, solutions, and claims, and they communicate, right? So how do you help students develop these? If you think about each of them, you actually have to unpack them further. What does it mean to collect and analyze data? What do you do when you're collecting and analyzing data? So we broke these big abilities into sub-abilities. We have like 39 of them. And for each of those, we created rubrics that help students improve their work. But before they improve their work, they need to do the work, right? So what are the examples of activities? We're going back again to what you just did. This is actually a lab that students do before they ever learn about Newton's third law. They do it in a lab, and they come up with the law without ever hearing from a professor about it. Then later, when they meet the professor, they have a discussion. So this is what you just did, right? And this is the next. This is just a lab. The text is taken exactly from a lab. And this lab is done by college students and done by high school students. And so an example of a rubric for 2 abilities included in the design and conducting a testing experiment. It is the ability to identify a hypothesis to be tested, and the hypothesis was the forces are the same, to state it clearly, and an ability to design an experiment that will test this hypothesis. And so what does it mean that the experiment tests the hypothesis and has a high likelihood of producing data that will lead to a conclusive judgment? Usually students do not have one hypothesis. We did it here for simplicity. They have multiple. And if the experiment is such that predictions based on 2 hypotheses give you the same outcome, this is not an experiment that is likely to lead to a judgment, right? So from using these rubrics, they learn how to design the experiments and how to write about them. In each lab or in each activity, they will not have all 39 rubrics, of course. They will have from 4 to 6. They will use them to evaluate, self-evaluate their reports, and then the teacher uses those to give them a grade without any comments, just as rubric C1 is a 3 and rubric C2 is a 1. They can take these reports, improve them, resubmit, and once they redo them, the same goes for quizzes too, for any assessments, they get the grade that they deserve. So you see that it's a very different environment compared to a traditional physics course, and even to many reformed physics courses. So we have been working with the physics department, reforming these courses since 2001, almost 20 years. So this is the history. We started with extended analytical physics. This is the course for engineers at risk of failure. We moved to physics for the sciences. This bio and chem and environmental science majors. And we ended up reforming the course lab component of physics for engineers course. So we have over 1,000 students in Rutgers, New Brunswick, in these reforms. So example of the reforms in 193-94, this is the course for science majors. An interesting thing is that the course professor is my former student. He's a teaching professor. He's not a tenured faculty. Lab problem sessions are led by my students who are in their physics teacher preparation program. Sometimes they're undergraduates. They're all skill denial because they're learning it in my courses, and then the professor already learned that and is very skilled in it. And all course activities are coordinated. This is what the classroom looks like. So the picture on the left is students working in groups at round tables, and the picture on the right is a symposium. Some students at the table, some are walking. They're walking and talking to each other after a lab, discussing what different groups did differently. So this is the community's group work, community creation. And they're allowed to resubmit their lab reports and their homeworks without punishment. So we conducted tons of studies there, and I'll show you just a few. So this shows how their ability grows over the weeks. So the students who got 0 and 1, basically they don't know what it is and how to use it. 2 and 3 on the rubric, more or less, they have an idea. You can see over the weeks from lab 2 to lab 8, the number of the black bands increase. So the improvement is statistical, and you can look at different abilities and see the same improvement. they start by not knowing much how to do it. Over repeated exposure in the labs, they are doing very well. Some abilities are very difficult to develop, and they never reach this 80%. They're content dependent, and they're just objectively difficult. But remember, this was the course where all instructors knew what they were doing, were trained in it. In 2014-15, we started reforms in the laboratory courses. And interesting, this is a course, standalone course for engineers, lecture component not reformed, lectures taught by tenure track faculty. We have not touched tenure track faculty yet. We only work with teaching faculty. Lab sessions are taught by undergraduate majors. Why? Because to train them, these are not people, undergraduate physics majors. Because when we started, these were physics graduate students not skilled in that. The lab sessions went for 3 hours because they needed to do the lab, they needed to reflect on it, and they said it's too much. So graduate students did not want to teach in this course. Now we have undergrads, but these undergrads are physics majors who did not learn physics throughout. They learned it through traditional approach. So they're not really skilled, but they're very eager, and we've been doing it for almost 5 years now. But the person who runs the training meetings was either myself or Mike Gentili, who runs that 193, 194. We did not manage to engage any tenure track faculty in this process. Results show improvement. I'll show you a few slides, but not as much as in that other course. Although the students start much higher, you will see the bars, the black bars, they grow, sometimes they regress, but they start at much higher levels with different types of experiments. Our best results on communication, look, we get to almost 100%. Students being able to communicate the purpose of the experiment and the details. So these are very important for engineers to be able to communicate. We teach them that. But other than this, the improvement is much less. So we've been, as I said, we've been doing it for over 10 years until now, 13 years, in physics in Rutgers, New Brunswick. But then we started working with New York.
Yeah, so starting before the fall 2018 semester, we were approached by one of the teaching faculty at the Rutgers Newark Introductory Physics program, and she was interested in reforming all of the introductory courses there. So unlike here, where we have specific courses for physics majors and science majors and engineering, there they just have physics. They have 8 physics majors every year. So their physics program is much smaller than ours. So we get to work with the entire population. So I'm going to go over year by year what we did because it looked a little bit different in the 2 years. So in the 2018-2019 school year, this was really just a pilot, and we were working only in the lab course. So I taught 2 of the lab sections, and I completely reformed them using an ILI's lab curriculum. So using all of the things that we have seen and that Dr. Etkina was talking about. So these sections were taught by an IL expert. We did not train or bring any other faculty from Newark into this process that year. And to see if the changes were having the effect that we wanted, we looked at the E-class survey, which I'll be talking about a little bit later, and we looked at epistemology data, and I talked to students to see whether they were getting what we wanted them to, not just from the physics content, but also all of the mindset and the skills. So to look a little bit at how things were changed, I want to talk about what the traditional labs looked like and then how we changed them. So the traditional labs were one experiment done every week. They had 2 hours to do the experiment. The students were working in groups, but those groups were working in complete isolation from each other. They came in, they worked with their 3 group members, and then they left. The students were given very, very explicit instructions. There was no room for thinking about what they were doing. They were told not just what data to collect, but also how to analyze it. And the goal of every single experiment was just to verify something that they had been taught in lecture. So these were very, very traditional labs. What we designed when we came in is that each week, their lab was a sequence of observational testing and application experiments, like what you saw here today. We would start with an observational experiment, we would break, we would talk about what we had learned from it, then we would go into a testing experiment. So the goal was really to make sort of a narrative across the entire lab course where we are developing knowledge. The groups worked by themselves, but then afterwards they would come and they would share their findings with each other. So we were trying to build that community. students were asked to design their own investigations. We would give them a particular goal to achieve, something to design a test of a particular hypothesis, or just to observe a phenomenon, and they would come up with how to do that for themselves. And the goals of these experiments were varied. We had observational experiments, testing experiments, and application experiments. So here is direct text taken from the labs. So you can see in the traditional lab, you were told exactly what to measure. You were told exactly how to vary the voltage. You were told exactly what to graph. And there was no room for thinking. In our ILS labs, we were just giving them the goals. So design an experiment to observe this phenomenon. This is a little bit what they look like when they are working. One difference between the Newark campus and the New Brunswick campus is the Newark campus is very ethnically diverse. So we have a very different student population than we have here. While they are working, they are constructing whiteboards. And as you can see, we have many of the representations that Eugenia was talking about in these whiteboards. So they're using energy bar charts, they're drawing sketches, they have tables of data, they're writing out what they observed in words. So we are reinforcing that they're using all of these representations. So even the students who aren't that strong mathematically have something that they can be contributing to their groups. The data sources that we used last year, we used the E-class, we gave it at the beginning of the semester and we gave it at the end. Unfortunately, only my sections gave it at the beginning. So for all of the traditional sections, we only have the post-class data. We also looked at student evaluations to see in their own words what they were thinking. And I talked a lot with students. There were some structured focus groups, but I became a point of contact with students. One of the things that I learned immediately was that they didn't really know who to talk to if they didn't feel that things were going well. A lot of students said they didn't know who was writing the old labs, they didn't know who to complain to, they didn't know anything. So I became a point of contact where students would just unload all of their concerns on me and I'd figure out who to send them to. So the E-class is the Colorado Learning Attitudes in Science survey, specifically for experimental physics. It consists of 30 Likert-style questions, which you answer ranging from strongly disagree to strongly agree. These are statements about your attitudes and beliefs in experimental physics. And it's important to note that experts do not strongly agree with all of these. Some statements experts disagree with. So for example, one of the statements is, I don't need to know how the equipment I'm using works in order to use it. Experts generally disagree with that statement. But some of them experts agree with. And some they're mixed on. So for example, some of them are like, I believe that everyone can succeed in physics experiments. That experts generally agree with, but less agreement than other things. So the important thing to note in using the E-class is previous research has shown that in a traditional course, E-class scores generally go down. So students have more naive understandings of science after going through a traditional course than they did beforehand. So in my class, in the reform sections, we saw that there was no significant change. So we did not see the decrease that we saw in traditional classes. And even though we don't have the pre-class data, we can compare the post-class for the two and make the assumption that they started at similar levels. And what we see is that at the end, my students were significantly more expert-like in their beliefs than the traditional students. So we can infer that the traditional sections did show the decrease that has been shown in the research, while the reform sections stayed roughly the same. However, in using the E-class, the authors generally don't say to just look at the overall score, but to look at the individual items that are changing, because those tell you whether the reform is having the change that you want it to have. So we looked at which specific items improved. So there were 5 specific items that we saw improvement in, and all of them very closely aligned with what we were trying to do with the idealization of the course. So the first thing I said is that when trying to do an experiment, I try to understand relevant equations, so they're not just being given information and plugging things in and just working mechanically. They said when doing experiment, I usually try to think up my own questions to investigate. They said that working in groups is an important part of doing physics experiments. They said the primary purpose of doing a physics experiment is to confirm previously known studies. This is actually one that experts disagree with. And we saw that our students disagreed with it more after as well. And this is because we introduced the language of observational experiments and testing experiments and application experiments. This is one of the main things that we want students to take away from our course, that we don't just do experiments to confirm things we already know. So we were very happy that we saw that. The other thing is that when they said, when I'm doing experiments, I try to make predictions to see if my results are reasonable. Again, we are very, very explicit about the role of making predictions in testing experiments. So we were glad to see that they agreed more with that at the end than they did at the beginning. I want to show you some of the things that students said about the course in their anonymous surveys at the end. So we see both general attitudes and also very specific things that improved. So students said they learned a lot more. Some said they learned more in lab than they did in lectures. Some said that it helped them figure out how to design experiments to prove if a hypothesis was wrong.
Notice that they didn't say how to prove my hypothesis. They said to prove that hypothesis is wrong. So this is a real physics dream just to hear that.
And we also saw that it made their interest in physics grow. So here's a very long quote, but it actually encapsulates everything that we wanted the students to say. So I will read this just because it might not be the easiest to see in the back. But this student said that many labs, particularly in physics, can feel mundane, simply being given a lab guide, following the procedure, and then writing a lab report about what you found. Generally, they are not infused with the spirit of discovery and experimentation because it's a procedure someone has already done multiple times with the same result. This instructor encouraged us to ask questions, form our own hypotheses, and test our own experiments, and then, and this was an important point for them, explain what we had actually physically observed and what that truly means. I was shocked to find how much I could enjoy this time. That was the thing that a student actually said about this course. So that was the first year. And again, this was just in a very small section of only the lab part of the course. We did not touch the lectures. We did not touch the recitations. This year, we did everything. So we dipped our toe in last year, and then we just dove head in. So this year, we are coordinating the larger meetings, which are the lectures, the smaller meetings, which are the recitations, and the labs. All of the instructors in the introductory physics program are involved in this. Again, all of them are either graduate TAs or teaching faculty. There are no tenured faculty working with us. But that's just the population of the teachers who teach the introductory courses at Newark. We assisted in the preparation of basically every course material. So we were making the slideshows for the lecture instructors. We were still designing the labs. We made exams and we helped with the quizzes. We even helped grading the quizzes and exams. I think Etkina wants me to mention that we did that on New Year's Eve last year because that was when the exam was given. We ran workshops to train the entire introductory physics faculty. So at the beginning of each semester, we had a longer training session where they were introduced to the IL philosophy and the IL approach. And then I ran weekly trainings with the lab instructors, specifically on the labs that we were doing, similar to what happened here in New Brunswick. So those were the weekly meetings. Unfortunately, they weren't as long as they are here in New Brunswick. They weren't even as long as the labs that they're teaching, so that's something that we're trying to work on. I also engage in mentoring and observation of the lab instructors. I chose to focus on the lab instructors because, as we'll see, most of them had never taught before. So they were novices and they were being asked to teach in this very sophisticated way, so they did need a lot of support. So that's where my attention went last semester. So I would observe them in class, I would help them in class, and then we would discuss what I saw afterwards. The data sources, we're still using the E-class. I used instructor observations to see how the TAs were developing in their teaching. So there are copies of the observation protocol that we used at every table, because I'm going to talk about some of the items in a little bit, and they're a little bit too small to see on the slides.
So just open on the second page. The first one is,
Yeah, so
is
go to
the
the second
cover.
page.
Yeah.
You will see the instruments that we use to actually measure teacher feedback. At the end of the semester, I gave the lab instructors surveys about how they felt about their teaching, whether they thought they'd improved or not, and what they wanted from us in terms of training in the coming semester. And we have student work. We have all of the quizzes they took. We have their exams. We have their lab reports that we have not yet had time to analyze. So as I said, in the fall semester, my focus was on training the lab instructors and teaching them to use the IL approach. Similar to the undergrads who were teaching the 229, 230 labs, these instructors had never seen IL before. They were introduced to IL a week before they started teaching their classes. So this is honestly a much more realistic implementation of IL at an institute that does not have union. So this is what it would look like more if a different institute wanted to take IL. So that's why we're so interested in what's happening. 4 of the lab instructors were new teaching assistants with no previous classroom experience. They were brand new teachers. 1 lab instructor was a non-tenure track faculty member. 2 lab instructors were part-time lecturers. I did not have the chance to analyze and observe them so much because of their schedules. It was very hard for me to schedule time to meet with them. Most of them were only on campus while they were teaching, and they conflicted with other things. So my analysis is going to be on the 4 TAs and the non-tenure track faculty member. So the training session consisted of 1.5 hour long meetings once a week. Our labs are 2 hours, so again, that's shorter. We couldn't actually have them work through the entire lab as students. We had to sort of mix the pedagogical instruction and the training them to actually do the experiments that they'd never seen before. So not ideal, but that's what we were given. So to measure whether the lab instructors were actually improving in their teaching, we used the observation protocol, which combined 2 different measurements. So the first one is the Reformed Teaching Observation Protocol, which is called RTOP. And the other thing we used were domains 2 and 3 of the Danielson framework of teaching. These 2 measures were chosen because both of them are designed for reformed, student-centered instruction. So we felt that they meshed very well with what we wanted to see the teachers doing. So the RTOP is on pages 3 and 4. If you want to take a look at, these are the kinds of items that I was looking for while the lab instructors were teaching. So it has 3 basic sections. One is lesson design and implementation. We were looking more at the implementation aspect of it because we were writing the labs. The lab instructors just had to implement them. But there was a lot of variation in how they implemented them. So this was still a useful part of the rubric. The second part is on content. So this is on both propositional knowledge and procedural knowledge. This is asking, did the teachers know what they were talking about? Did they connect what they were teaching in the lab with what was happening in the lecture, or just to general phenomena that students know in life? And then the third part is the communications, the classroom culture. So this part was also very important to us because one of the things that we want in the IL approach is for the classroom to become a learning community. This is a very difficult thing for teachers to create, especially when they've never really taught before. Danielson is used primarily in secondary education, but good teaching is good teaching no matter where it takes place. The difference between the 2 that I saw in using these rubrics is the RTOP gave a lot more flexibility on were they doing these things? Were they trying to engage students in conversation? And I found that the Danielson was more helpful in piecing together how well they were accomplishing those things. So here's what we saw. All 4 of the TAs showed significant improvement on both measures that we used. And the non-tenured VNTT showed no change whatsoever. So I want to talk a little bit about what their classrooms look like so we can see what these numbers actually mean. So the non-tenure track teacher, his class generally started as such. He would walk in, he would give the goals to every single experiment students were doing that day, and then he would let them do their experiments. He did not bring them together to talk about their results afterwards. He didn't try to foster any community. He just let students go. It was the most traditional teaching that I saw in this course. And I talked to him every single time after I observed him. I tried to get him to break them up, and he gave me a whole bunch of reasons why you can't teach that way. So he was very, very resistant to change. TA1, this is the TA who improved the least. He held very traditional beliefs about the instructor's role in the classroom. At the beginning of the semester, he would begin every 2-hour lab session with a 20 or 30-minute lecture about the material before they had even touched any of their equipment. That started to reduce. I wish I had a graph of like the amount of time he spent lecturing over the semester because it did decrease. But by the end of the semester, he did agree with the philosophical approach, but he still had a lot of difficulty actually implementing it in the classroom. TA2, this TA started higher than all of the others and improved the most. So she was the most willing to adopt student-centered practices, and from the first lab, she was already trying to do what we wanted them to do. She was trying to get students to discuss with each other. She was trying to create this community. So all of my work with her wasn't on getting her to do the things, but on giving her the skills to do them well. So that is why she showed the most improvement. The other two TAs fell somewhere between TA1 and TA2. So briefly, I want to look at the E-class results that we found from last semester. Again, we didn't see an overall change in any of the students, so this is much better than last year where only my students stayed the same and all of the others decreased. Here, even with these novice teachers, we didn't see the decrease that you typically see. And we saw significant improvement in 10 of the 30 items. So a lot of these are attitudinal. Things like, if I wanted to, I think I could be good at doing physics research. I enjoy building things. Nearly all students are capable of doing physics experiments. There were some that were related to what we actually tried to teach them. Things like, I don't need to understand the measurement tools. That is one that they were supposed to disagree with, and they did. More at the end than they did at the beginning. There were 4 items that we saw decreases in, that students became more novice-like. And I want to talk about those because I have hypotheses about what actually caused those changes. So the first 2 are kind of related. The first item is that if I'm communicating results from experiments, my main goal is to have the correct sectioning and formatting. So this is one that experts disagree with. The second is that if I am communicating results from experiment, my main goal is to make conclusions based on my data. So those 2 are kind of opposites of each other. My main goal is just make it look like a physics paper, or my main goal is to communicate what I learned. And we saw that students thought that they had to do formatting. And my observation of this is that in the classes of the NTT and TA1 and TA3, they were very, very strict about formatting. TA1 would begin every class by talking about the reports, and here's what you have to do to get a good grade. This is the thing you have to include. He gave them very procedural steps to do well in lab reports, which could have led to this feeling that the reason they weren't getting good grades on their lab reports was because they were formatted incorrectly, rather than because they were not demonstrating the scientific abilities. The other thing that they decreased in is that if I don't have a clear direction for analyzing data, I'm not sure how to choose an appropriate analysis method. So this seems like a negative thing, but I'm not entirely sure it is. I think the reason that this decreased is because students had never really been given a lab without specific instructions to analyze data before. So it's not that they are less confident now than they were, it's that they didn't know how difficult it was when they started. So that's my hypothesis for why this one decreased, is that before they just didn't know that they didn't know how to do this. And now they do, and now we can work on improving. And then the last one is the physics experiments contribute to the growth of scientific knowledge. This is one that physicists obviously agree with. We saw that students decreased with this, but it was not across the board. Students in the sections that I taught and in the sections that TA2 taught, at the end, 10% of them disagreed with this. All of the decrease in this came from the other instructors. So this has to do with how they were actually implementing the labs. As I said, the NTT wasn't actually allowing them to develop their knowledge. It was just experiment after experiment after experiment. In TA1's class, he was very confused with islands. This is our pre-service teachers take 2 years to learn ISLE before they're actually using it in the classroom on their own. these instructors had a week. So this is not surprising, but this is, I think, why that particular response decreased. So overall, what we've learned in the past 2 years is that change is very difficult, especially when you're changing everything all at once. We found that the presence of an IL expert is essential to the reform process. There were a lot of things going into this that we did not know that we needed to do. For example, we did not know that we needed to prepare the slideshows for the lecture instructors. So had this been going on at another institution, had they not been in contact with myself and Eugenia, that would not have been done. They would have been stuck. So there needs to be someone who actually understands IL in order to fix any problems that come up. We learned that instructor buy-in is absolutely necessary. We found the instructors who embraced the IL philosophy were the ones who showed the quickest improvement and the ones who adopted it most faithfully. We found that the teachers with no teaching experience were generally more willing to embrace the new method than teachers who had teaching experience. Part of this, we think, is due to the habits they had developed over the past years. Habits are hard to break. Part of it is also that the teachers with no experience did not know what wasn't possible. They didn't really have a framework for what the classroom should look like as an instructor themselves. So they were more willing to listen to me and not tell me, oh, you can't do that. You can't do this thing. We found that even during the transition, even when things are still a little bit rocky, there are measurable improvements in students' beliefs and attitudes. Countless times before in research, we found that there's always going to be student pushback whenever there is a change towards more student-centered teaching. Engaging in these kinds of activities, not having a teacher stand up here and talk at you, doesn't feel to students like learning. So a lot of them, in their course evaluation for the lecture last semester, said she wasn't teaching us. So there's a lot of that kind of pushback. But what we found is that if the teacher was more expert in what they were teaching, and in these styles of teaching, that pushback decreased. I got no pushback of that kind from my labs. And from what I have so far this semester, I'm not getting the same kind of pushback from lectures that she did. And we found that in Newark specifically, our largest barrier has been scheduling and time. There has been very little time allocated to us for training lab instructors. We cannot get them to pay for instructors to come in on weekends or over breaks. So all of that training is strictly voluntary, especially when working with PTLs. We have contract things to get around that they will not pay for, so we cannot require PTLs to come in for training sessions, and they will not give me a training session for lab that is longer than the lab. So that has been the largest barrier that we've had. And those are references.
Thank you. Thank you.
Questions, comments?
So it's really exciting to see like the pictures that you all shared, because it reminded me, I'm a high school teacher, and it reminded me of like just really good classrooms I've seen in secondary education that I think we forget, like once we get to the college level. And then also the students that I'm working with this semester, to hear them talk about creating more quizzes and all of that kind of stuff. And I was really excited. I was wondering where they're getting it from, and they're getting it from this approach. You mentioned, you specifically said that on the Newark campus, you talked about the demographics of the students, and I was wondering if it was a reason for that.
I think there is an institutional reason. I don't know what it is.
Oh, okay. No, I mean the reason you brought it up.
Oh, just to say that this is working with a different population of students than the one that we have here.
Like saying that it works with all types of students?
Yes.
Oh, okay.
Yes. Particularly, we find that the math background of the students in Newark is not as strong as the students here in New Brunswick.
Okay.
So this goes back to the universal design aspects of IL, that it works in a number of different environments.
But Josh said that we graded exams. So the exams consisted of multiple choice and open-ended. And the course professor said, you know, I don't have time to grade for 100 open-ended. So Josh and I, we would sit and grade them. We have rubrics and we use, and I was personally blown away by what students wrote. I would never expect those students who never took physics, who were taught by people not skilled in our method, only doing it for the first time. What the students were writing was the most amazing, really, truly amazing. We have a rubric that doesn't score for correctness, but it scores for clarity, consistency, and evaluation. They need to be clear in what they were doing. They need to have more than 2 representations, and they have to be consistent, and they need to evaluate their answer. So you can have the right number and still get a 0. But you can, if you're getting 6, it means that what you did is amazing. And they would write 2 pages with small words trying to explain what they did and how they did it. And you know how difficult writing is for physics and engineering students. This is not what they're strong at. And their ability to express themselves was amazing. So.
Other thing to me that was not surprising is that the professor would be the toughest to train, just because I could see that if you've already been teaching, you just feel like I'm gonna do this and I'm not gonna concern myself with anything new. So it was kind of exciting, I think, to see that most of the TAs were so willing to jump in.
Yeah, and that was the interesting thing, because especially TA1, at the beginning of the semester, he gave me a lot of pushback, not just in terms of the teaching, but also in terms of the physics. A couple of the things that we do very differently. He, butted heads with me about, no, this is wrong. That, stairs do work on you as you're going up them, was a thing that he tried to convince me is true. But at the end of the semester, all of them said that it was a very good experience for them, and that they were excited to keep going. So even in the day-to-day, when you're working with, when you're trying to train people, it can always feel very frustrating. But at the end, they were excited. We've heard that other faculty members are interested in what we're doing, and possibly when we're done with this, we can look at some of the higher level courses.
I wanted to ask how your coding of the explanations of the communication, how it overlaps or aligns with the claim evidence reasoning that is done in GSE.
Good question. Well,
because it sounds like there are real points of alignment, right?
they are and they're not. Because we do not, what we teach them, that you do not, in physics, you do not try to find evidence to support your claim. You try to find conflicting evidence on the molecular. So the testing experiments, the purpose of a testing experiment is to disprove. In the lab that you saw, for Newton's third law, it says, remember, the goal of the testing experiment is to disprove the hypothesis, not to prove it. So the only thing that you can say at the end, I failed to disprove it. I did 15 experiments and I still could not rule it out. So that is contradictory to searching for evidence to support the claim. However, once they move to the application experiments and the models have been tested, they'll say, well, this works because of that and this works because of this. So this is different. But when you're making a new claim, when you are devising a hypothesis, you do not search for support. For example, I'll give you an example. You put you take a wet towel and you rub the table, right? So it dries. How do you explain it? Well, air sucks up moisture. I can prove it. I'll take a hairdryer, it will dry faster, right? While if you try to think of disproving it, you will find an experiment very quickly that will disprove that air is involved at all, right? So that's the point of contention. When do you use evidence to support your claim? And when you're trying to look for contradicting evidence. And so what in the rubrics, it says, state the hypothesis clearly. That is kind of your claim in a way, right? And then design an experiment whose outcome you can predict using this hypothesis, right? So we teach them to make a prediction. We teach them the difference between a hypothesis and prediction. In most science books, they are used interchangeably. And they call a hypothesis what is in fact a prediction, or they call a prediction what is in fact a hypothesis. we teach them a very clear difference between them, and we teach them that the goal of the testing experiment to get the disagreement between the prediction and the outcome. So that's an ideal thing. And if you can't get a disagreement, you just need to repeat again.
So I was just wondering, is this modeled on the Socratic method of teaching by any chance? Like, I mean, is there similarities, just kind of like in the way you're not like telling them, you know, how to do the experiment per se, you're kind of letting them make their own mistakes, and in the process teaching them principles like we were talking about falsificationism or something like that. Instead of just like, you know, telling like this is how science works, kind of let them.
Yeah, and in a lot of ways it is similar. Especially the big struggle that we've been seeing in Newark is the lecture classes. How to integrate this into a lecture room with, you know, 200 students. So that in that situation, having a Socratic dialogue is very, very difficult. But we do want to keep the elements of this. So the most important thing for us, or for me when working with the teacher, because I must have missed this in the slide. One of the other things that I found is that small pieces of pedagogical advice were much more readily adopted than larger philosophical things. So telling the lecture instructor that, you know, students need to work through their, yes, I did forget that one. So telling the lecture instructor that students need to work through all of the problems before you show them solutions, that is sort of a very tangible thing that you can do. You need to give students a certain amount of time before you actually go through the problem, or they're just not going to be engaged at all and they're just going to be received passively. That's a lot more implementable than vague discussions of sort of active learning and the philosophy behind it. But it goes a little bit farther than just Socratic dialogue, because we also combine all of these experiments into it. Even in the lecture, we have videos of experiments, or we conduct experiments in class when they involve simple materials. So it's not just that we're sitting and we're reasoning our way to the answer. We're always going through this process.
And an important thing is that when we prepare, like I make a list of activities for lecture, right, from our active learning guide. So these are the activities they do when they are with 200 people. And they work on the activities and they discuss them, and then there's a clicker question. But the difference from Socratic dialogue, that Socratic dialogue just leads students, right? Here, it's not simple leading, it is providing a framework to always think about phenomena in a certain way. So this process, observe, find patterns, think about them, try to test your ideas, try to rule them out, examine assumptions. It repeats again and again and again. And so it develops a habit of thinking about physics in this way. They see something, ideally, and they need to ask themselves, is this an observation? Is that a pattern? Is that an experiment that somebody did? Is that or is that a hypothesis? This is a hypothesis. Was it tested experimentally? How was it tested? Like, you know, Iraq has weapons of mass destruction. This is a hypothesis, right? How was it tested?
Also, I'm sorry, this kind of like a sub question. Are you guys thinking about implementing this through like online learning or anything like that? Is that in the works at all, or because I'm sure that the structure is a little bit different?
We have modules posted online, but they are to be implemented in the classroom. And one of my current students was teaching an online course in the summer using it. And we don't have, we have videos that are videoed and we have questions, but we don't have a platform through which to administer it. I think, and there are many reasons. First, you know, we're just not experts in this online learning, to be honest. Secondly, you have to work as a community, and I don't know how to make a community. You need a mini community of a group where people trust each other, and then you have a maxi omega community of the whole classroom where people trust each other. You need to create this mistake-rich environment that you talked about, but how do you do it online when people have never seen each other and they don't know who they are? I just don't know. I'm not an expert. I think it would be great, hypothetically, but it just not the right person for that. Yeah.
Yeah, so thank you for this. This is really interesting. And it seems like it's a, what you've got is a real generalizable model, at least across science, right? So I guess what the question that I was thinking about is, so in the challenges and the training, are there particular kinds of physics conceptions that you find that people struggle with that or provide opportunities for development? I mean, you know, we didn't really get into any of that, but like, how does the content intersect?
Yes. So first I want to say that while here we only presented our work at the college level, all the students who I trained to be physics teachers, now it's over 150, they're doing it in high school physics classrooms. So it's much easier to do it in high school because one person is in control of everything, and they have not developed the bad habits. They are brainwashed into this method by me and all people who I work with who are graduates of the program. So they relearn physics in the program, and they relearn the language and the symbolism and approaches. So the physics faculty, and I've been running workshops on IELTS since 2001. We were in the process of developing the materials, and we started running workshops at the American Association of Physics Teachers meeting. So for almost 20 years. And there's certain things, as you said, that are extremely difficult. And one of them is a cross-cutting concept in NGSS, is the concept of a system. So the system approach, which we promote throughout all topics in the course, is supported by physics faculty, but not really understood. And once we start applying it, that's what Josh mentioned briefly, you know, in the area of energy, it's very difficult. And the same, so this is one thing. Another thing is the language. Physicists developed a secret language that they understood, that they understand what it means, while it sounds completely anti-physics. For example, right? I don't know who to ask. Who is not afraid? Who is comfortable to say what your weight is? So mine is, let's say, my weight is, let's say, 200 pounds, right? It's my weight. I am very passionate.
Very dense.
Very dense, yes. So I'm passionate about it. It belongs to me, right? You all agree that your weight is your problem. But in physics, we say weight is not mass, right? Weight is a force. The force does not belong to you. The force describes an interaction. So there's a huge contradiction between the term weight and the concept of a force. All teachers, starting from elementary school, say weight is not mass, and yet mass belongs to us, and we talk about our weight and we measure it on the scale, right? So our discourse about weight prevents us from understanding the nature of force, and then the professors who use the term weight, they say, my students think that objects carry forces. Of course they do, we carry weight, right? So that's just one of the examples. So in our materials, we made a ton of changes to the language. Now imagine that you have been using a particular vernacular for 30 years, and then somebody comes and says, don't say weight, don't say heat. The same thing, you know, when you talk about heat, it's like something that is in the object. That is a thing that can be transferred, right? While in fact, heat is none of those. And when you think about heat as an object that can be transferred, you cannot do thermodynamics, for example. So there's a lot of things that all physicists understand it, but when they talk about it, that's not the message the students get. So changes to the language is very important. And one third change I will say that is very difficult is once you are an expert in something, you forget how you were not an expert. So when physicists model physics problem solving, or any mathematical procedures, they skip steps. I'm sure math professors do the same. And then the students are lost. How do you get from here to there? Well, I don't know how he got from here to there, so I must be stupid. So one of our approaches is not to skip steps, which is very, very difficult. And this takes us to the next thing, is that certain things that we take for granted, like, for example, what is a minus sign? Minus in math is a minus, right? You have negative numbers and you have an operation of a minus. In physics, the minus sign can mean at least 6 different things. It can mean direction. It can mean subtraction. It can mean absolutely nothing if it's a negative sign, the charge of a negative sign. Has nothing to do with anything. It's just like a color, right? So paying attention to the difference between mathematics and physics, and mathematics is a huge thing. So, and I can go on and on and
Right,
on.
but we're not gonna.
Yes.
We have to close up, so thank you so much. Next week, we're going to continue in our science education work. Michal Zion is coming over from Israel, and so join us then.